It's you see the video here on the right side. We have the video live. I can show you. Yeah. So we have a Raspberry Pi. This is version 3. I think is a model B+, but doesn't make much difference. And then we have this our Kryptor already connected. And I put here another one just to show, you know, the way you can connect to a breadboard. And as I mentioned before, you have just 2 pins, which is the power and the ground, and plus the other 4 for the SPI on the back. So that's all you need, which are at the end of the board. And these are already here, of course, connected. Now, so physically, once you have these 6 wires connected, that's it. That's all you need. The board at the moment is powered. Raspberry Pi it's running. You can see probably from the LED at the bottom, red LED. And you can actually also visually see there is one LED on our Krypto which is blinking. This is the heartbeat LED, which gives an indication that yeah, there is no problem and the unit is up and running. Now on the left side of the screen you will see a terminal window, and I'll basically now, I think I need to restart the connection. Yeah, we can connect to the Raspberry Pi, and as in the usual way. So I'm using SSH and connected directly to the Raspberry Pi. Now we are in. We can move to the directly where I loaded the Kryptor file. Now those are, so in here you can see the main command line interface executable. So through this one we can now run some commands. Now there are some files which will be used for end-to-end encryption left in there for another tutorial. So actually I can't remove them. So now in the directory we can see only the CLI executable, and one of the first things we can do is actually just run it. So this will give you a list of all the options, all the commands that actually you can run, which is a combination of most important symmetric and asymmetric encryption with the generation of the keys, both symmetric and asymmetric, and then there is a random number generator, and you can actually change the speed. Now default is 2 megabit per second as mentioned, but you might want to lower it for some specific reason. Then we have the symmetric ECC, and now I will go through some of those more in detail. We have hashing, you can do CBC encryption, and some more commands. You can also control some of the LEDs to, maybe if you want to build some application, have some visual feedback, and some example. Now one thing you can do straight away to see everything is fine, for example, is this M command. So you can actually run it, and what you will get is small text with the vendor and products, and very important is this serial number. So this is basically linked to that unique serial number mentioned before that every chip has. So every single Kryptor PCB board will have a different serial number, and with this command you can actually extract that number. This will be useful, and I will come back in maybe another video on this, because when you want to install our HSM core, you need to basically get access to this serial number. Now another simple one we can see, so something visual that you could have a look. for example, we could use the LED command, and I can switch on one green LED which is in a on the board, which will be, I think, on top side. So now running this command, that's it. So the LED now is on, and this of course could be used, while programming, just to have a sort of visual feedback connected to your operation, your program, or the kind of solution you are implemented, and with a simple 0 we can switch it off. That's it. Another one quite nice, also for seeing the operation, what's going on, you could actually put -1. This will activate. Now the green LED is used to monitor the traffic through the SPI. So whenever there is traffic on the SPI, the green LED will blink. And now, for example, if I go and run M, I guess it's probably not very visible in the video. Well, I see it live, but we'll see in the final video if it's still there. Anyway, this will blink quickly depending on the traffic going to the SPI, so we can leave it down there. And then we have also the heartbeat, actually, the B, which is by default is active, but I could disable it. So now you see it's blinking there. Now I disable it, and now the LED is not blinking anymore. So the heartbeat is off, in case you want to switch everything off. And of course you can bring it back. So this will activate. That's it. So those are really basic things to just verify the functionalities. And now we are gonna go a little bit more in details. And one important factor here is this. So as mentioned, this device is basically providing professional encryption functionality, so the HSM, and we wanted actually to pack it in a very small form factor and make it available at very affordable price. So that's why we reduce also the speed of the SPI, but you can get access to all those functionalities that are now listed here. And we have now in this version, and this is actually also, you can refer to this version 1.2, so we will update both the firmware and the command line interface. So most probably on the final version, which will be shipped to the buyers, we will have a higher version with probably other features, and but anyway, we will see. Now, one important thing, so in this version there are inside, as mentioned before, there is some internal flash, and actually you can go back quickly here. So we have some internal flash. Now this flash is used for various reasons, also to store all the FPGA cores, but part of those are actually used to store the various symmetric and asymmetric keys that we can generate or load from outside, from a file. So there is a certain amount of memory available. For this version we have actually four slots for symmetric and asymmetric, and this is the reason of this. So I can, for example, generate a symmetric key, and I can store it in one of the 4 available slots. So the index is 0, 2, 3, so 0, 1, 2 and 3 are the valid number. And I can also generate key pairs, so an asymmetric pair of keys, which again will have 4 different slots. And then I can read as well the key. Now, so keep in mind, for all your usage and for the whatever solution you want to build around, so you can generate and use different kind of keys, and of course up to you the way you will generate or actually the way you will use them, because the generation is done inside the hardware and the keys are stored in the hardware. Then there is another important one, is what we call the root key. So that's an asymmetric key, which we can, think about like a master key. So the point is in all this asymmetric key is that the private keys are not visible, cannot be printed and cannot be extracted. There is no functionality to extract a private key, and that's very important for security reasons. So the device will be generating and holding the most important keys, which are the private keys. And if you would allow to extract a private key, that would be already a weakness in the solution, because of course unwanted third party could get access to that private key. So we don't want that. Okay, let's try now something. Enough talking, and we want to do some practice. So let's say one thing we can do easily is let's view with the command R. Let's view the content of the slot memory. So the symmetric key number 1, for example. So that's a second key, 0, 1, 2, 3, and that's a 0. This is a brand new device, so memory is empty and nothing has been stored. So what we can do, let's generate a key. So we use the symmetric key. So we use this -G, we generate a key, and we ask the HSM to generate the key and automatically store in the slot number 1. Done. And now to verify, we simply read back. So before the slot, of course, was empty, and now we have, in this case, 128 bits symmetric key. So this one now can be used through the CLI to encrypt, for example, a file. And of course now we can generate for all the 4 slots and then use them as we want. So that's just a very basic, simple example. And now let's say we want to do the same with an asymmetric key. So in case asymmetric is generation is the capital G, and read is a capital P. So if we go and read the slot number 0, for example, we have all zeros. And as you see, this is a double size because we used ECC 25519 and at 256 bits. So the asymmetric keys are a bit bigger. So now we can actually generate, let's say, one asymmetric key. So we use the switch capital G, and we store it directly in the slot number 0, so the first slot. And now we go and read, and as you see, we have a key. So this is actually generated automatically using our true random number generator, and then the key or the number is actually passed through the ECC. So this is the algorithm ECDH, or actually ECC, and the symmetric point is found, and then it's used as a public key. So 1 is the private key, which is not displayed, and this is of course the public key. So this can be used for our application. Now a simple example we can do is, let's say we want to encrypt a file with the symmetric key. So we have a symmetric key number 1. So for encryption, I will just now clear out a little bit, just show. So for encryption, we have the switch E as encrypt, and we can encrypt a file and save it on again on external file. So in this case, we could actually create the file, the plain text file, and we say this is my secret message, then we save it, and we give the name plain text, for example. Okay, let's now try to encrypt the file. I just had to reset the camera, so the position should be a little bit different from before. So to encrypt a file, we are going to use the option E, which will accept a file name, and then it will output an encrypt file, so a file. And for that we'll use the option O to actually output directly to a file. So the syntax will be, let's say, to encrypt using option E. The file is our plain text, which we created, and then we're gonna use actually the key number 1. So we use the option W, which means with key. So we use it as a target, the symmetric key from slot 1. And then we're gonna use the option O to write on a file encrypted, and we execute. So the file is there, and in fact now we can even verify that the file is encrypted. So the display, this is a string of hexadecimal numbers, so hex number, and that sequence represents the plain text encrypted with the symmetric key from the slot number 1. Now we are gonna do the reverse operation, so we're gonna decrypt it, and for that we're gonna use the option D, decrypt file name, and then we're gonna write the decrypted file directly. So we use -D, we decrypt the file encrypted using again the key from slot 1, and we're gonna write the file decrypted. So what we are doing again, we are decrypting using the key from slot 1, symmetric key from slot 1. We are decrypting the file name encrypted, and we're going to generate an output, a file called decrypted. This is done. Now we see all files are in there, and now we can actually display the file decrypted, which, as we can see, represent exactly same content as our plain text. So we took the plain text, we encrypted with the key, symmetric key 1, and then we decrypted the encrypted file with the same key, and we got the original plain text. Okay, thank you for following this. This is already a first introduction to this HSM product called Kryptor, and in the next videos we're going to go a little bit more in details with other functions provided by this Linux API. Thank you.